Okay.
Okay, so my ref plan is continuing plans that we've been trying to follow, but with some disorganized interruptions, jumping around in different directions. There's something that I really think that I understand at the moment that I really want to try to explain to you. So this is all growing out of my recent attempts to understand Grothendieck-Teichmüller theory, the design d'enfant, or designs, as I've been calling them. And this is Grothendieck-Teichmüller theory, but it's growing out of Galois theory. And so yeah, those Mathematica programs that I know you love, that really helped me to understand. Like I came up with these pictures, that I drew with Mathematica, but that really helped me to understand how the Grothendieck-Teichmüller action really works on these designs. And so that was like really helpful to me, and I'm trying to build on top of that. I'm trying to use that as a launching pad for understanding all sorts of other things, and but particularly all sorts of Galois theory things, which to me is sort of everything, actually. But so there's at least two directions that I'm going in here. One is sort of backwards, and one is sort of forwards. I mean, the forwards is sort of very ambitious stuff, trying to understand things that I really don't understand yet, things like motives and the Langlands program and stuff like that. So that's one of the directions that I might be going. But there's also the backwards direction, more back to the foundations, trying to really understand things that I'm perhaps supposed to already understand, but I'd like to understand better. And so there are basic things in algebraic number theory, like the Artin reciprocity theorem, which has to do with the splitting patterns of number fields and stuff like that, and Kroneker's Jugendtraum. And these are things that I feel like I already understand, but I would like to understand them better. So these are near the foundations of algebraic number theory. And so that's my vague plan. My vague plan is to build on things that I feel like I already understand about the design d'enfant, and go both in ambitious directions and into more foundational directions. But there's a pretty specific idea that I really want to focus on right now, because I feel like I'm close to understanding it. So this idea actually starts out in pure homotopy theory. Actually, as soon as I said that, I realized that's not quite the right way to say it. I'm going to start out this idea in pure homotopy theory, but it probably is really good at some point to recognize that that pure homotopy theory is not where these ideas started. These ideas probably really did start more in algebraic geometry and number theory, but then people realized that you could abstract from the algebraic geometry and the number theory, and you could create this very abstract, beautiful, and in some ways easier subject of pure homotopy theory. It kind of crystallized some ideas in a pure way. And so I'm going to start talking about something that sounds like pure homotopy theory. Mm-hmm. But that's only because I'm going to be slightly ahistorical about it. If you're less ahistorical about it, if you're more historical about it, then you realize that this really does have roots. What I'm going to do really does have roots in algebraic geometry and number theory and stuff like that. It really has roots probably in Galois originally. So the idea that I'm going to try to think about here is basically this. what happens when you have a composite of covering projections? A composite of covering projections. So I'm imagining a space A and a space B and a space C, and this covering projection from B down to A, and this covering projection from C down to B. And I just need names for everything here, so I'm going through the alphabet. This covering projection from B to A, I'll call that D. Covering projection from C to B, I'll call that E for now. And it's very important that there's this composite covering projection, which in my convention, I guess I would call that ED. And so like I said, the question is, what happens when you have this? And the approximate answer is that you get a very interesting short exact sequence. There's a very good reason why you get an interesting short exact sequence. I mean, a short exact sequence is like a twisted mixture of two things, a twisted mixture of a quotient and a sub thing. A quotient thing and a sub thing. And that twisted mixture is corresponding in some way to the, the way that the composite projection ED is a mixture of the two things you're composing, the E and the D. So, so how's this going to work? The way this is going to work is we're going to take the automorphism group of D, and that's going to end up being the quotient group. And we're going to take the, and I have to, I have to give more precise descriptions of what do I mean by the automorphism group of a map here, et cetera, et cetera. The automorphism group of E is going to be the subgroup. And the automorphism group of the composite, ED, is going to be the center of this short exact sequence, the twisted product. I guess in some abelian situation, it would be like a twisted sum or something like that. But we're interested in both non-abelian and abelian situations. So, we may see situations where we might want to call it a twisted sum, but also situations where we want to call it a twisted product. So that's supposed to be a picture of a short exact sequence. I guess other people write it a little bit differently, but I already ran out of room to put the little 0 at the top. So maybe I'll just write it this way. That's a picture of a short exact sequence. So what do I mean by the automorphism group of a map? I mean, in this case, I mean that we're sort of taking the slice category of, spaces over the, we're thinking of the, we're thinking of the domain of the covering projection as an object in the slice category of spaces over the codomain. And we're taking its automorphism group as an object in that slice category. So in other words, right, so what does that mean? That means like if you have let me draw a picture of an automorphism of D. So D is this covering projection from B to A, and automorphism is like an invertible map there. Like, has the appropriate property. It sort of commutes with, in a certain sense, commutes with D.
Luckily, I know what you mean by that.
There's a little commutative triangle that two of the legs are D and one of them is F. And it is a sort of degeneration of a commutative square. So it's some kind of commutativity. So,
Okay, I think I get it.
yeah, but there's some important things that I didn't say. They're important. There are probably some important assumptions here that we will need to mention, although at some point we might want to go beyond relying on those assumptions. But there are important assumptions to mention here. But before we try to even put in any assumptions here, let's start trying to see if we can figure out how to get these maps to work. So, for example, let's start. Am I saying this right? Let's start with an automorphism of E.
Mm-hmm.
And it says that we're supposed to get an automorphism of ED from that. So do you have an idea how to do that?
Yep, we compose E with D.
Yeah, that's very simple. Okay. Now, what about the other one? Is the other one just as trivial? How do we get the other one to work?
Sorry, I probably could get it, but I'm busy writing this thing down.
Okay. So, yeah, I'm not sure there's quite as slick a way to just instantly say what the other one is, but maybe this might be somewhere where some of the assumptions come in. So what am I trying to say? That these are covering projections, but I think what I actually want to do is I just want to have them be normal covering projections, meaning that, you know, the covering space should be a normal covering space. It should in the Galois correspondence between the subgroups of the fundamental group of the codomain and the covering spaces of the codomain, in that Galois correspondence, the domain should correspond to a normal subgroup. And, you know, I'm not sure exactly what the standard terminologies are for that. Maybe that's called a normal covering space, or maybe it's called a Galois covering space. I'm not quite sure, but it's a fairly basic thing to assume. And so does that help in any way in
Let's see, sorry.
clarifying how to get from the automorphism of ED to the automorphism of I guess we also didn't, I'm not sure we said instantly anything about why that process for getting the automorphism of ED from the automorphism from E. I didn't notice anything that made it instantly clear that that's an inclusion of groups. But for all I know, maybe it is. I don't know.
I don't know either.
But okay, the general pattern here, it doesn't seem not that surprising, right?
Well, now I'm wishing that, like, this normal condition,
Yeah,
were re-expressed in terms of these kind of pictures you're drawing now, instead of talking about normal subgroups of pi1. It feels like there should be some, I mean, it sounds like you're gonna have to come up with some way to use that's in terms of these pictures here. And now I'm just wishing I knew.
well, it's all to do with the fact that we've got we're going to have we're supposed to have a surjective homomorphism of automorphism groups here, and associated with a surjective homomorphism, there's a normal subgroup. So that's basically what's going on. see, I mean, if we weren't dealing with normal covering projections, then there'd still be a whole bunch of stuff that we could do, but a lot of the stuff that we could do would start with cooking up some associated normal covering projections from our non-normal covering projections. But so right, I mean, the idea is that
is a normal
yeah,
covering space one that, like, could we say that, let me try to say it specifically, could I say that like E is a normal covering if and only if for every choice of D, that map from aught ED to aught D is surjective? Is that what you're trying?
I'm not quite sure. And I'm also not quite sure whether I'm focusing more on D being normal or more on E being normal.
Yeah, well, that's
but
true.
I mean, so a normal covering space, right, is the one where the fibers are not just acted on by the fundamental group, but they're actually quotient groups of the fundamental group.
Yep.
So that's what's going on here.
How is that relevant here?
Well, I mean, when you talk about fundamental groups on the one hand versus automorphism groups on the other hand, they sound like very different things, superficial.
Mm-hmm.
But they're really, really closely related. I mean, so like if you start out with a fundamental group, how can you think of it as an automorphism group? Well, there's this device called the universal cover. That's a machine for being able to think of your fundamental group as a
Automorphism group of a universal cover.
yeah. And what was the question I'm supposed to be trying to answer?
Just
Yeah.
go at it any way you want. I was just, so yes, I agree that when you have a normal covering, the fiber over the base point is actually a group.
Right.
Yeah.
Right. And it's, you know, it's a quotient group of the fundamental group of the base space of the codomain.
Mm-hmm.
And so right, so one of the things that's going on here is that the order in which I named those things going through the alphabet is probably the correct order. You know, I started with A at the bottom, and then B and C going up. So the idea is, right, you're supposed to think of this as upward direction, as sort of progress here. Right here, and this will really show up, you know, more when you're acknowledging that there's, you know, algebraic geometry going in here, and you start thinking about the algebraic things corresponding to these geometric diagrams. But right, I mean, so you've got the space A where it's sort of very coarse, but then you make progress by putting in finer distinctions and getting to B. And then you make more progress by putting in finer distinctions between the points, and you get to the point C, where points are distinguished more finely. So this is a refinement of spaces. And and yeah, so I am going to be leaving a lot of work for the audience, which is us, to do, but I think that's okay. I mean, right, the idea is that there's this progressive refinement process going from A to B and then to C, and this gets manifested in this short exact sequence in the way that, you know, first we have this quotient group D, which is again somewhat coarse. And then well, what am I saying? So we have we think of D as a process going from the trivial subgroup. Sorry, yeah, we go from the trivial subgroup, which the trivial group, which is sort of the automorphism group of A over itself. And then we make this big step to the automorphism group of B over A, and that's the progress made in the step D, the first step, and that progress is recorded. It's manifested as this Galois group of D. So that's the quotient group in the short exact sequence. And then the second, the progress of the second step is manifested in the automorphisms of E. But then you have to, you know, you have to think about how these steps don't occur in isolation. Rather, E follows upon D, and it's an extension of the progress we made in D. So, you know, the automorphism group of ED, that's that thing that this is a manifestation of how the, you know, how those two steps combine together to give you this twisted product. Again, this some of this may sound more familiar if when we start talking about it in terms of Galois theory of fields and stuff like that. But there is an interesting pure homotopy theory viewpoint here, so I wanted to sort of mention it that way. So
well, it sounds like I've got a lot of work to do, because I don't know why this map is, I don't know why the top map exists. I don't know why it's,
there is a lot of work, but I'm hoping it's very easy. But
I don't know why the second map is surjective. And you're saying, I guess, that everything will work out fine if maybe like all the coverings are normal.
yes,
coverings.
yes, and even if they weren't, there's something that you could do to change it back to this case.
Okay, well, I feel like pressing you on this, but maybe this isn't what you wanted to.
Well, no, you could try. I'll accept pressing if there's, you know, specific trenchant questions.
Well, for example,
yeah,
like the surjectivity of the second map, the map that I actually know what it is.
Yeah.
It would be nice to see what that had to do with the normalcy of one of those. And I don't even know, as you said, I don't even know for sure which one of those two coverings, either D or E.
Well, I mean, keep in mind, right, that it's right. Normal subgroups correspond to, you know, their normal subgroups are almost synonymous with kernels of surjective homomorphisms. So the key correspondence here isn't between the normalness and the surjectiveness, right? It's the normalness and the homomorphicness. The fact that this projection is a group homomorphism, whereas, right, the non-normal analog of that is when you have a group mapping down to a coset space. So the coset space isn't even a group, so you can't even ask for it to be a group homomorphism, but you still have the surjective map from, you know, from a group to a coset space, and it's, you know, and there's a special coset, which is like the base point. The special coset is the subgroup itself. Well, once you decide which.
I have to resist. I have to argue against that because
Yeah, go ahead.
I just, over on the right of your slide here, I had
Yes.
told you this procedure for getting from this automorphism called G
Yes.
to, wait, let's see, sorry. Sorry, I meant I don't mean the second map. Sorry, okay. Yeah, never mind. Sorry. I meant
Okay.
yeah, okay, maybe I understand what you're saying. Yeah, okay. Sorry. Okay, so the first arrow.
Yes, the first arrow. Yes, that's the inclusion homomorphism. Yes.
Yeah, that's obviously a group homomorphism because of how
Oh, and you're asking why is it normal or something like why is it?
No.
Yeah.
Well, okay.
Why should it be normal? Yeah.
Okay, so you're saying for the second one, somehow the normality is going to give us this group homomorphism property. Yeah. Anyway, I just don't yet see it. I have to do some calculations or something. What I'm really hoping for is that, like, you can take this normality condition,
Yeah.
and translate it into some property that's easy to write down using these type of diagrams that you're showing here. That is, like,
That
some
probably
kind
is.
of
Yeah.
universal property here, some kind of niceness property of these, expressible in the language of these diagrams here.
Yeah, there probably is some way to do that. There's some way to clean this up, but I'm really not. Yeah, I mean, I have this idea that. Yeah, I'm leaving out the details. I'm leaving out here are the ones that are, are not terribly clear in my mind at the moment. But I also feel that they're not that crucial. That they are homework type assignments. That basically, if you have a composite of unwrappings, then I'm sort of saying, there are good reasons why you might as well assume that they're both. These covering projections are normal coverings. You might as well assume that, and it'll make it easier to describe things. Like it'll make it easier to see how you're getting a short exact sequence of groups. I think what would happen, right? I think what would happen if you had non-normals covering projections here, I'm guessing you'd still end up with, if you did it the right way, you'd end up with a short exact sequence of groups, but it would really just come from the sort of normalizations of the coverings, but it would come. It would be like it would probably be a short exact sequence of concrete groups, rather than a short exact sequence of abstract groups. So I think I'm just sort of trying to avoid getting into the extra thing about the short exact sequence of concrete groups or something, because I don't even know what, is there something good about thinking about short exact sequence of concrete groups? I don't know.
Yeah. Let me ask a different.
Yeah.
And so.
Yeah.
So in this Klein geometry business, where you think of subgroups of a group as types of figures,
yes,
in geometry, where the larger group is the symmetry group, then the normal subgroups give you figures of this special sort, which I like to think of as, them as like figures that are so symmetrical that you can name them without pointing at anything in your geometry. So they have like an invariant
yeah,
name.
something like that.
I've managed to, like,
I mean, they're sort of saturated with respect to joining them together with any other thing that they're in the same orbit with.
Right, yeah. So I've had some luck getting students on people who are acting like my students online to
Yes.
learn to like normal subgroups from that point of view. Like I was talking about, like subgroups of symmetries of a cube, and saying like, oh, like the subgroup that fixes a vertex
Yes.
is not normal because you got to point at the vertex to say which one. But if you say like the subgroup that only sends each vertex to its either itself or its antipode, that's
Yeah.
that's
Yeah.
one you can say without pointing to anything in specific. So okay, that's a warm up. And so then I was just asking, can I ask, is this normal covering idea related to that idea? Is it like the same idea?
Well, probably. Let me put it this way. So, Kleinian geometry has a lot to do with thinking of non-normal subgroups and symmetry breaking, reducing to a non-normal subgroup as putting extra structure on your geometry, like an extra graffiti or something like that, that mars the perfect symmetry and cuts it down, breaks the symmetry down to something smaller. But the role of normal subgroups is not so much in symmetry breaking like that. At least not most of the time. It is a very unusual, special kind of symmetry breaking. But normal subgroups more saliently have to do with forgetting stuff than with remembering structure or imposing structure. So, I mean, right, forgetting stuff that's like when you have a quotient, a quotient group. It's like the original Kleinian geometry might have something like, corners and vertexes, or points and lines, or something like that. But then in the quotient group, in the geometry corresponding to the quotient group, you're kind of like saying, we're going to completely forget, some of the stuff or something. We're going to have some other stuff that's left over. So that's part of what's going on here. That these covering projections, you're sort of forgetting these distinctions. Let's see. The fiber is a fiber of stuff or something like that. But down at the quotient level, you've sort of forgotten something. But I don't know. There's all sorts of things to say here. But I do have the feeling, right? I have a feeling that I'm not positioned to do a good job of discussing any of that today.
Okay. So
it's more like I'm trying to pretend that we do already have a good understanding of that. And I'm leaving this ridiculous amount of conceptual homework for the audience to understand this, to understand the whole idea of how a composite of covering projections, a composite of normal covering projections, gives you this short exact sequence of sort of Galois groups in this homotopy theory sense. And so now I'm going to proceed and try to apply this this philosophy. And like I say, we're going to revert to where some of these ideas may have come from. We're going to revert to geometry and arithmetic, algebraic geometry and arithmetic. And so now we're talking about something like Well, now, I mean, right, if it's going to be algebraic, it's going to be something like A is going to be a field, and B is going to be an extension field, and C is going to be an extension field. And I guess these are going to be Galois extensions or normal extensions or something like that.
Okay.
And right, so once again, you have these Galois groups, the automorphism group of the extension keeping the base fixed. And you know, so this is kind of the, you know, via the usual contravariant philosophy of algebraic geometry. The algebra and the geometry are sort of opposite of each other. You know, we get a short exact sequence this way too.
Mm-hmm.
And it's basically the same idea.
Mm-hmm.
And again, there may be some fine print that I don't want to worry about, but I'm not going to worry about it. So let me give an example of this, okay?
Mm-hmm.
And again, I hope we don't have to squint too hard to pretend that this actually is an example. But so let's take A to be right. One way that we may have to squint is I may have said these are fields, but we may actually use commutative rings here or something like that. But it hopefully should still work. You know, and at some point we're going to be taking étale fundamental groups or something like that. But define, well, we'll see. So let's take A to be the rational numbers adjoin an indeterminate X and an inverse for X, and also 1 over 1 minus X. Okay.
Uh-huh.
And let's take B to be basically the same thing, except with Q bar. The algebraic closure of the rational. So the algebraic numbers.
Mm-hmm.
And I hope I'm not getting everything backwards and upside down more than it should be. And then C at the top should be, well, first of all, notice that this first step here was very arithmetic, very arithmetic. But this second step is going to be very geometric. At least if you squint at it the right way. So it's going to be something like, I want to say something like Q bar join X and 1 over X and 1 over 1 minus X, but then a whole bunch of other stuff.
Like what? Just arbitrary?
Well, for example, square root of X, cube root of X.
Okay.
Basically anything you can think of to put in there. You know, you should put in the sort of solutions to all algebraic equations you can think of that don't ramify anywhere except for a, well, I mean, we've already sort of punctured the spectrum in 3 places.
Yep.
I mean, like if we pretend for a moment, you know, right, Q bar is somewhat dense in the complex number. Just pretend for a moment that it is the complex number. Then if that were true, then the spectrum of this thing would be sort of like the Riemann sphere with 3 punctures.
Mhm.
And so then there's just all the extra stuff that can add, like, square root of, is that true? Am I right? I'm thinking that, that if I adjoin the square root of x, that will morally qualify as a covering projection, because at first you might say, oh, but it's it's defective at x equal to 0. Oh, and but we've already eliminated x equals 0 from the spectrum by putting in 1 over x. So there's some.
Yeah, so the algebraic functions that have branch points only at 0, 1, and infinity, something like that.
Yeah, now some people have a lot of fun trying to give an explicit description of this thing at the top in terms of Poisson series.
So your goal, so that you're supposed to be putting in all of them. That is not just some of them, well, not just your favorite ones, but like it.
That's right. That's right. We are playing the game of construing a thing that is morally a fundamental group, but construing it as an automorphism group by creating a universal cover of which to take the automorphism group and have that be this very concrete way of thinking about this fundamental group. So yeah, so that's what's going on here. This is another time that we're playing that game of being able to explicitly think of something that's morally a fundamental group, but being able to explicitly think of it as an automorphism group by basically taking a universal cover, except that here we're really doing it in this upside down algebraic sense that, instead of taking a universal cover, we're just taking some sort of algebraic closure, but it's, it's some sort of restricted algebraic closure. It's this very Poisson-like thing. On good days, I remember how that Poisson series stuff works, but I don't think we have to worry about it here. But yeah, so this is the basic idea of, and again, I got this from, this was, I mean, I already told you that I learned some stuff from reading this very introductory paper by Thomas Willwacher, or whatever his name is, Willwacher. But I think I understand it better now by thinking of it this way. I don't think he said it this way explicitly, but I think this is all that's going on. I think what's just going on is this first step where you do all of the arithmetic stuff, and then the second step where you do all the geometric stuff. And the result is that you get this short exact sequence, which is going from. So I hope I'm saying this right. It's something like the universal profinite completion of the free group on 2 generators. That should be like the automorphism group of this geometric thing, right? So this is like the algebraic geometric version of the fundamental group of a Rice punctured Riemann sphere. And so that is included into this thing. Yeah, the thing that is the automorphism group of the composite extension.
Does that have a name? Something.
I don't know. That's a good question. I don't know. Also, is it just a, is this just a split semi? Is this just a split short exact sequence, or is it interestingly non-split? And am I
Well,
supposed to know the answer to that? Am I supposed to know the answer to that question?
I don't know. What's the third one called?
The third one is called the absolute Galois group. You know, the absolute Galois group over the rationals, but that's the absolute Galois group. Right? You can see pretty explicitly that the absolute Galois group is just the automorphism group of this extension of B as an extension of A.
I guess so, yeah. Somehow all the X stuff doesn't matter for that purpose.
That's right. The X stuff is just along for the ride. When I originally wrote this down, I started out writing just Q and Q bar. And then somehow I realized that it wasn't really working. I didn't have the right thing. So yeah, so I started padding it out with these X's stuff, because for the second step, you really need those X's. That's, you know, that's where you're going to get this geometric stuff in the second step. So
what's funny is that very often people write down short exact sequences as a way of like understanding the thing in the middle. You say, oh, the thing in the middle, it's basically just made up out of these two parts.
Yes.
But here it seems like what you would like to understand might be, well, people love to say they want to understand the absolute Galois group. And the thing on the,
I mean, there's all sorts of
middle, it sounds like you don't even know what it is or care what
it might be very important. It might be very important. But the reason why I'm not worrying about the middle so much is because I mean, I do care a lot about the middle, but in a way I sort of care about it. But what I really care about this short exact sequence is that, right, you should read a short exact sequence as being, and I should say that, you know, I mean, right, I mean, one of the ways in which we've changed from our pure homotopy theory situation is that these are not just abstract groups. These are some profinite topological groups. And, you know, what does that mean? Well, I have some ideas, but I'm just, for the moment, I'm just sort of pretending that, you know, I didn't even notice that. So again, pretending that this is just a short exact sequence of ordinary groups. So what, right, there's a very good philosophy about how to think of those things, right? So you should think of those as being two functors from the quotient group into the two category. Well, maybe I should say the two category of groupoids or the two category of groups. It depends on how you want to think of it. I guess you should think of it as the two category of groupoids, but it just so happens that all the values of this two functor are, you know, groups that are groupoids that happen to have, you know, just one isomorphism class of object. So, right, that's what a short exact sequence of groups really is. It's a two functor from the quotient group into the two category of groupoids that for some reason just takes takes the unique object. We're going from a one object groupoid into the two category of groupoids, but it just so happens that our one object is going to another single object groupoid under this two functor. And so that's what's going on here. So, right, so I mean, so right, so again, we discussed a little bit about whether this short exact sequence is a split short exact sequence, and you know, I'm probably supposed to know whether or not it is, but for some reason couldn't tell you right now whether it is split, but being split is basically correspond to this, this extension being a semi-direct product.
Mhm.
And also, it corresponds to the two functor from the quotient group to the two category of groupoids. It corresponds to that two functor being a very strict two functor in some way.
Mhm.
Whereas in greater generality, it's more like just a good strong two functor. So
yeah, it would be nice if it weren't split, because then you'd be getting, I mean, it might be nice because then you'd be getting some, I mean, a lower brow way to say what you just said is you'd be getting some two co-cycle on the absolute Galois group, that taking values in this other group.
and you can think of that two co-cycle as this coherence of the functoriality or something like that.
Right. So anyway, so that's like a thing you might use to somehow investigate the absolute Galois group.
Yes.
If it's, if it's split, then I guess it's just acting on the absolute Galois group is just acting on the universal.
Yes. So I think pretty much no matter what, it's acting by strict automorphisms of the subgroup. But those, all those automorphisms together, they don't satisfy the homomorphism property in a strict way unless that two co-cycle is trivial or a co-boundary or something like that.
Mm-hmm.
So this is what I think I've learned by reading Willwacher's reading just the very, very beginning of Willwacher's introduction to Grothendieck-Teichmüller stuff. And then thinking about it for a while, and then rethinking it in a way that maybe seems more systematic to me.
Mm-hmm.
So, so down here, right, it's the absolute Galois group, but it's acting on this free group on two generators, except that everything in here is profinite. So, well, so I mean, right. So I mean, that is a resting point. I mean, that's yes.
Yes.
But now we don't have to rest too much. I mean, but I have to figure out what to say next. I mean, so that's supposed to be a big exclamation point. That this for me is a much clearer way of understanding Grothendieck-Teichmüller theory than I have had before this. And so I'm asking myself all sorts of questions about this. So what is the mystical significance of the fact that first we do the arithmetic extension and then we do the geometric extension? Partially because, right, one of the things I want to do with the arithmetic extension is I want to, as much as possible, reinterpret it as being a geometric extension, morally or literally. So I'm not sure what to make of that, but this is what I think is going on here. This is what I think is going on.
Another question I have is what does Baez's theorem have to do with this stuff? Seems like this stuff you could do without using Baez's theorem at all, whereas
well, okay, so I actually get a little bit confused because there seem to be two theorems that some people seem to call Baez's theorem, and they sound very different to me, but maybe they're really secretly the same theorem or something. I'm not quite sure. I mean, so it might be obvious that they're the same, or maybe they're just two separately very important theorems. So I mean, one of them says that the action of the absolute Galois group on this universal profinite completion of the free group on two generators, that action is like faithful in some sense.
Okay, that's good.
But
that answers my question about like what do you get out of Baez's theorem?
But is it true that is it true that some version of Baez's theorem that we think of as the more familiar version of Baez's theorem implies this faithfulness? What am I trying to say? So there's this thing sometimes called Baez's theorem that says that that every cover, I think that's right. What am I trying to say? No, every something like every field that is defined over the, what am I trying to say? Every curve that is defined over the algebraic numbers. Maybe every non-singular curve that's defined over the algebraic numbers or something like that.
Yep, can be
realized as
something that's ramified over just these 3 points over the projective line. Yeah, that's.
Do we have some obvious or non-obvious connection between those two things that I sometimes see it associated with Baez's name? Is there an obvious way that you use? I'm not quite sure, but there's a good question there. Yeah.
We'll just bet that first Baez's theorem implies this other Baez's theorem, but I don't see exactly how. The first one is
if it does imply, if there is a direct connection here, or then I'd really like to know what the connection is exactly. And it almost feels like there's a connection, but I don't quite see it. It might be really obvious, but I just don't see it. Not yet, but so this is the basic conceptual picture that I'm attempting to have of Grothendieck-Teichmüller theory. I mean, this is just the beginning, motivating foundations, because people do all sorts of other weird things, but this is the basic motivating foundations for me. And so now, one of the things that I want to do here, I mean, right, this is a very big, abstract, universal sort of thing, but this same structure should show up in very concrete examples. Like, let me try to talk about some examples here. So, like, let's consider something like, right? There's this. Right, that's right. There's this regular Gaussian design, and it has these two irregular quotients, one of which looks like this. I'm using some drawing style here. I don't remember what drawing style it is, but one looks like that, and the other one looks like I'm doing this right. And they're not strictly isomorphic, but
Mhm.
they are in the same orbit under the Grothendieck-Teichmüller group, under the Baez action. So yeah, those are the two right there. And so let me try to sketch out how this is analogous. Well, it's sort of a, this and all of designs, all concrete, specific concrete designs fall out of this general abstract picture that I was just describing. But now I want to show that.
By the way, I mean, the general abstract picture described doesn't superficially have anything to do with designs, and the designs, they usually are brought in by mentioning the version of Baez's theorem that's it's not the one saying that this action is faithful, it's the other one you mentioned about branch covers. So it's sort of interesting that
All right, I think that sounds
two
important.
statements of Baez's theorem, one of which seems to make the abstract picture of the exact sequence be powerful.
Yeah.
One of which makes designs powerful. So there's like a gap to be bridged there.
Well, but
Which presumably gets bridged.
well, let me bridge it in one way.
Mhm.
Well, so one way is just remember that those designs are concretely the continuous actions of that universal profinite completion of the free group on two generators. So right. There's some nice stuff going on there. So I mean, in other words, right, we're exploiting some Tanakian principle there. That if to give an action of the to give this strong action of the absolute Galois group on this universal profinite completion of the free group on two generators, to give that action should, from the Tanakian viewpoint, be equivalent to giving an action of the absolute Galois group on the
set of actions.
on the category
Sorry. Yeah, sorry.
on the category of continuous actions of this profinite group. And
yeah, that's very nice.
And right, and we
Sounds
think
painfully abstract until you identify those continuous actions in this very concrete way.
Right. And those continuous actions, that category of the continuous actions, again, the part of the whole Tanakian viewpoint is that is a theory, that is a symmetric, monoidal, locally presentable category. So it's a theory in this very nice doctrine. And the Tanakian viewpoint is kind of saying that the interpretations between these theories are really the exact same things as these continuous group homomorphisms between these profinite groups. So we're getting the absolute Galois group to act via interpretations, via auto interpretations of this theory, and it's the theory of a torser of the universal profinite completion of the free group on two generators. And we may seek to make it sound more interesting and less just going through the motions than just saying that it's the theory of a torsor of that group. There may be more specific things that we can do to make it seem more interesting. And now, yeah, there's all sorts of other things to say here as well. And but I don't really know how to say it. I mean, you were bringing up the issue of how concretely these designs end up being the same things as these continuous actions of the, and I mean, that has something to do, what am I trying to say? That, right, these designs, they look like, it looked like they were created with a pen or something like that. It looks like there's these one-dimensional things on these conformal canvases. But what those one-dimensional things, those are somehow real things on these complex canvases. So there's something going on here about that I don't understand yet, but it's probably going to be important. Something about how thinking about the ramifications of these number fields at the Archimedean prime. That's connected in some way that we need to clarify with, the concrete nature of these designs, that they are, they look like with these pen things are somehow telling us about these real things that have something to do with, I think they have something to do with the ramification of these number fields at the Archimedean prime. But I'm right, I'm barely even making sense when I say that. But I think what I said there is eventually going to make sense. But it's just another thing that what you started talking about made me think.
It's also just a more obvious thing that the dots in the design are indicating ramification of what you're calling the
that's ramification on the
geometrical.
Yes, that's right.
Stuff, the geometrical part of it. And then there's ramification at primes, which I can't see from looking at the designs, but maybe you can see it. Right.
But there's all this interaction that I'm not completely understanding yet. This interaction between this very abstract ramification of the number fields at the primes, and this more palpable ramification of the designs at these vertexes in a very geometric way. Anyway, let's proceed. We don't understand everything, but some things that still seem mysterious will eventually seem less mysterious. But already a bunch of things are beginning to suggest themselves. So, right. So one of the things I wanted to do here is to take this this very abstract general picture of this big short exact sequence involving the absolute Galois group and the universal, the universal profinite completion of the free group on two generators. But I want to, with my particular example here, I want to connect this to a much smaller short exact sequence, which may show us what's going on here. So what am I trying to say here? I'm trying to say that so I'm going to draw another one of these composable pairs of field extensions or commutative ring extensions or something like that. So at the bottom, I'm going to have I'm going to have the rational numbers I hope this works. I hope I'm doing this in a somewhat correct way. So it's really the same base, but I'm just going to go travel upwards much less dramatically, much
Uh-huh.
tamer extension. Yeah. So what do I want to say? Right. Okay. So the first step should just be something like, I think it's going to be Q. Well, here's where I wish I could, have at my fingertips all the results of the concrete mathematical calculations that I was doing with this design. Because I remember, right, it was something very simple. It was like the only irrational number that was showing up. I can't remember whether it was the square root of 3 or it was the fourth root of 3. It was something really simple. I think it might have been just like the square root of 3, or it might have been the square root of -3 or something like that. I'm going to say the square root of 3. But I wish I could remember. Let me put some, question marks there because I'm not sure I'm remembering this correctly. But right, the point was that, right, I mean, we were getting some non-trivial Grothendieck-Teichmüller action, some non-trivial Belgian action. But it was, it was like the whole absolute Galois group was just being coarsened down to this 2-element group. And it was like the Galois group of this square root of 3 or something like that.
Uh-huh.
Yeah. I wish I could remember, but I think it might be the square root of 3, but I at some point I should clean this up and find out exactly what it was. But so we're gonna just do that arithmetic extension. And we're gonna have, no geometric extension. So we're just keeping this stuff here. And then at the next step is where we're going to do, right. We're following the same pattern. The first step is the arithmetic step. The second step is the geometric step. So the second step should just be, whatever the thing is that I wish I could write down explicitly what it is. It's good, it's just going to be well, I'm also getting slightly mixed up because, right, these pictures that I've drawn over here on the right-hand side of the page, those are evidently supposed to be these genus 1 pictures. Those are supposed to be toruses.
Mm-hmm.
But part of the trick when I was working with them in Mathematica was I found these, you could double cover, they double cover these genus 0 things.
Mm-hmm.
And those are also somewhat photogenic Gaussian designs. And so there's all sorts of places here where I may be making stupid little calculation mistakes, but they're not that serious. It could be that what I'm drawing here is actually more like the genus 0 stuff. Maybe I'll need some other. I'm not quite sure.
Uh-huh.
But so up at the top here, we're going to have what? We're going to have. So we've already joined whatever arithmetic stuff we need. But then we're going to, right, then we're going to join just a little bit extra in the nature of geometric stuff. I'm guessing it might just be like one indeterminate y and right. I mean, you can get something just like, y squared equals x cubed minus x or something like that. But I have found that's not quite the right one to do here because, I mean, that is the correct elliptic curve. It's just this very square parallelogram. But I mean, that would only give some double cover, whereas this looks like it's supposed to be some maybe 18-fold cover. Or something like where are the actual, right? I think the actual things here are something. What am I trying to say? They're supposed to be lozenge shaped. I think those are actually right. I think those fundamental things would be like there or something like that. Or how many of these are there? It looks like maybe twice. Maybe there are 18 of those, or are there 36 of those? I'm not quite sure. Are you any good at counting?
No.
Oh.
Sorry, those lozenges. Those lozenges have half the area of the bigger squares. If I wait, by a lozenge, you mean those diamond things? Or
Yeah, like one lozenge would be like this
okay, yeah.
diamond thing.
Okay. Well, they have half the area of the yeah, they have half the area.
Half the area. So maybe there's 18 of those.
Uh-huh.
On the other hand, if I dream the genus 0 case, I would only need 9 of them, maybe. I'm not quite sure. But it would be I mean, it would perhaps be some 18th degree equation. So it'd be morally similar to this, right? It would be giving the same canvas, the same genus 1 curve, but it would be it would be covering it 9 times. So there'd be this. There's some calculations here, obviously, that I haven't straightened out, but in principle, it would just be some very relatively minor thing here. I'm
confused for one thing, because that new if you think of that new thing as a new elliptic curve, the green stuff is giving you like a new elliptic curve. So that elliptic curve is isogenous to the Gaussian elliptic curve. Is that true?
Let me think. Okay. Now you're making me confused too, which probably proves that I didn't really understand what I was saying. So yeah, what am I trying to say here? So those are the lozenges. Well, the lozenges are like. Am I saying this right? Right. No, the lozenges are like. Okay. Let me think. Yeah. Well, say your question again.
I'm not sure it's the best question, but
yeah,
are those green? So if you think of that array of, let's see, if you think of that green drawing as like describing an elliptic curve.
Yeah.
Is that elliptic curve isogenous to the Gaussian elliptic curve? That is, which means, I guess, just is it? Like,
it is, but well, wait a minute, something's confusing me here. Something's confusing. See, that would be true, except you have to remember the way this combinatorics thing works here is. Let me see if I can draw it. So there's like a diamond there or something like that, and it's like there's like a green dot there and a red dot there, and there's blue dots like right there and right there. And the way the combinatorics of this works is that if you only have this one thing all by itself, then there's right, because of I guess you could say because of the color matching, this doesn't allow you to wrap it up into a torus. The only way that this allows you to wrap it up, into a sphere. So how would that work? You'd have, you'd sort of, seems right. You would, pull. So you would simultaneously pull the blues over the green to form a single blue, but at the same time, you would also pull the blues the other way over the red. And so I'm saying it would sew up into a into a genus 0 thing rather than a genus 1 thing by the combinatorics of the vertex color. So your question didn't quite parse because it didn't. In this game you never get the chance to perform that kind of identification because it wouldn't. The vertex colors wouldn't match. Does that help at all? I mean, just as an abstract conformal thing with vertex, if you did perform that identification, then yeah, it would just be like a Gaussian. Yeah.
Yeah, I was just like, yeah, I don't know. I'm confused. Yeah, so you're doing this genus zero stuff, but I guess I'm already confused by like, you got an elliptic. If you got like the Gaussian elliptic curve, it has this famous cubic equation defining it, presenting the branch double cover of the Riemann sphere, and then there are all these other elliptic curves that are isogenous to it. Are you now getting even more confused? You're thinking about one that is.
Oh, maybe I don't remember what isogenous means. What does isogenous mean?
It sort of means it's covered by or covered.
Okay, I thought you meant. I was stupidly thinking you just meant like it's isomorphic or something like that. But you were talking
about this one. Well.
So yeah, okay, right. It's isogenous to more things than it is isomorphic to, yeah. And it includes these things, yeah, these funny things. If I understand what isogenous means, yes.
Yeah.
And you were asking something about that?
I just realized I'd never thought too much about how, like, if you have an elliptic curve and another elliptic curve that's covering it.
Yes.
Then you should be able to get like like if the original elliptic curve was written down using a cubic equation, then the one that covers it should be being written by some higher degree equation, if you want to describe it as like a higher degree covering. And it sounded like that's what you were doing here.
Yes, and I mean there are all sorts of tricks that we could use here and mistakes we could fall into here. But I mean, like, using the complex multiplication aspect, that this is all, related to the Gaussian integers, you can, there are it really would be fun to work at, it'd be annoying in a way, but it would be fun to really work out, these things, I'm saying, oh yeah, there is some equation here and I'm not writing it down, but it would be fun to really work this out and, figure out exactly what it is. And I'm really not that far away from doing that, but
yeah,
but somehow I got dragged more into thinking about this in a conceptual way instead of thinking of it in this very gritty, mathematical way. So, yeah. So I'm kind of saying this down at the bottom here. We have this field, which is a little bit of a mix of arithmetic stuff and geometric stuff, except that the arithmetic stuff hasn't really got off the ground yet. All we have is the rational number. But then in the first step, we put in some just some interesting arithmetic. And then in the second step, using the arithmetic stuff that we put in the first step, that enables us to put in some geometric stuff. And so what am I trying to say? I think this intermediate field here is like what would be called I don't trust me on this, but it's something like the moduli field of the design. So this is going to give us one of those short exact sequences as well, but it'll be a very nice, manageable, small short exact sequence. So, it's going to look something like Z mod 2 as the quotient group. And then, right, in this case, it really is going to be a split short exact sequence because, basically, what am I trying to say? It's just going to be, it sounds right. Actually, don't trust me on it. But it's going to be, so what is it going to be? It's going to be Z mod 2, which is the arithmetic Galois group that's involved here. But then the subgroup is going to be this geometric Galois group that's involved here, which is going to be what? How big is that going to be? Is that going to be 18 elements or 36 elements, or what is it going to be? It's going to be I think it's like a 36. It's basically going to be the semi-direct product of, it's going to be this quotient of the Coxeter rotation group of the Gauss that's coming from the Gaussian integers, right? I mean, we have this. All right, let me think. Let me think what the. Let me see if I can get. Okay, so there's going to be. We have 9. Right, we started taking the Gaussian integers modulo 3. That's kind of what's giving us this 3 by 3 picture.
Mm-hmm.
So that means the additive group of the Gaussian integers is being coarsened down to just this 9-element group, this 9-element translations of this little grid. And but then what's going? Let's go. Let's see. But then there's 4 9 plus 36. It may actually be a non-split short exact sequence. I'm not quite sure, but I'm having trouble saying precisely what it is, but you're getting some idea of what it is, right? It's going to be this. It's going to be the. I want to say it's something like the Galois group of the design. So what do I mean? It's like the. I mean, we have this Coxeter diagram. And this sort of gives us the symmetries of the Gaussian lattice, including the translations and the rotations, and even the reflections, even if you include the whole Coxeter reflection group. But if you just look at the Coxeter rotation group, then it's just giving you, it's basically the affine general linear group of the Gaussian integers. And which is just a semi-direct product of the, the 4-element rotation group, the 1i, -1, -i, that little 4-element multiplicative group of the Gaussian integers that's acting on the translations of the Gaussian integers. And that's what's giving this Coxeter group.
Uh-huh.
But now what am I trying to say? Well, first of all, right, ignore the Coxeter reflections. Just look at the Coxeter rotation group. And we're trying to look at this design here. And so what's the quotient group? The quotient, right, the quotient group is right, these little lozenges. So right, there's an 18-element group there. Saying that, right? So, I mean, it's like an arithmetic Galois group acting on a geometric Galois group. Is that right? I mean, this. want to say something like the affine general linear group of the Gaussian integers. Sorry, there was supposed to be a 1 in there. You know, it's like AGL1 or something like that. What am I trying to say? AGL1 of the Gaussian integers. And then I think I want to say that modulo 3, if that makes sense. You know, I didn't want to put the modulo 3 inside on the Gaussian integers. I want to put it on the outside, that you got this group here. So I think this is the 18 element group. And then the short exact sequence goes like this. And so we're getting some sort of, we're getting some sort of involution of this group. And that is the thing that changes this into this. Again, I wish I could say this much better, but so what am I trying to say? I'm struggling with the concrete details here, but I hope you're getting the idea of the abstract big picture. That, right, for a particular regular design, we get this coarsening of the situation, of the coarsening of the situation that we had back up where? Up here.
Hold on, sorry, I'm gonna pause.
Okay. Okay.
Okay, sorry for that interruption.
Okay.
So
yeah, so I'm just gonna try to come up with, you know, wind up with some sort of punchline here. So basically, you know, I'm saying that I think I'm making progress in understanding how arithmetic and geometry fit together in this game. This game being, you know, Grothendieck-Teichmüller theory. And you know, from what I was trying to show you here with the particular designs, particularly Gaussian designs that I was fooling around with, you know, I'm trying to show that you know, that you can see how the arithmetic and the geometry fit together in concrete examples as much as you can in the abstract big picture. And the concrete examples are just kind of a, you know, little miniature version of the abstract big picture. And if you want to try to summarize how it is that the arithmetic and the geometry in fact fit together here, you could sort of say that the way they fit together is that the arithmetic is sort of acting as just another kind of geometry, but for some reason it's a step that comes first. So you have these extensions, and the first extension step, you just adjoin arithmetic quantities. But then in the second step, you adjoin these geometric functions that unfold or unwrap your space in a geometric way. And you know, so there's all sorts of good things to think about here. It would be a lot of fun if we have time to do a lot of these concrete examples and see what's going on. But also, well, and then, you know, there's all the other things we want to get back into, like the splitting patterns and art and reciprocity and things like that. But there is one sort of next mystery that, you know, now that I feel like I'm making progress on this mystery, there's another mystery that sort of seems to grow out of the answer to this mystery. And that next mystery is, you know, I seem to be claiming that, you know, in this game, arithmetic just appears as another kind of geometry. Well, but that seems like a mystery in itself. You know, in what sense is arithmetic appearing as another kind of geometry? And you know, maybe we have some clues about this, but still it seems mysterious in a way. So I'll just kind of quit there. Anything?
Okay, yeah, I like
Yeah.
that stuff a lot. It's one thing that's a little funny is that the example you keep looking at
Yes.
gets into maybe it's just Mathematica being dumb, but it gets us into the really complicated looking equations. Whereas this short exact sequence idea that you just described makes me optimistically feel that there should be some like, so I mean, you're like getting these little baby short exact sequences
Yes.
inside the big mother exact sequence. And it seems like there should be some babies that are like really easy to describe, easy to write down.
Yeah, I mean, I think they are. I mean, you know, don't forget that when we were getting, like you say, Mathematica does some dumb things, and you know, Mathematica was making, or you know, you can blame it on Mathematica, or you can equally blame it well on my incompetence in using Mathematica. That you know, some of the formula results I was getting just looked ridiculous. But when I cleaned it up, it really was, I think, the kind of thing that you're asking for. I think, you know, maybe it really will be worthwhile to do that example in particular, or a couple of other examples in some gritty but not oppressive detail.
Because it seems like if you thought about it from this new viewpoint, it might be easier. Like you could say, like, okay, I got this bottom field here, Q adjoin X, 1 over X, 1 over 1 minus X, and I throw in square root of 3. Now I can put in a new variable that obeys a polynomial equation that involves square root of 3.
Right.
I mean, so there are lots of polynomials like that you could try. I guess you're looking for one, you're part of the problem or whatever, so you're looking for one that's giving you something connected to the Gaussian elliptic curve.
Yes.
Whereas there would also be sort of non-Gaussian things you could do.
Yes.
So, but anyway, even with the Gaussian constraint, there probably is some way to get those polynomials sort of by pure thought, now that you have this new picture.
If I understand what you're saying, then yes, I think yeah, I think so.
Yeah. So anyway, it would be, so if they're like manageable examples to do by hand and pure thought, then it would be fun to see some. Yeah.
Yes, I would like to do that. I hope I managed to come up with manageable, nice examples that we can follow through on with that.
Yep.
Okay.
Okie doke. So
that's it.
Nah, I don't think so. I mean,
okay.
Just talk about, but I think I'll quit. Yeah.
Okay, that sounds good.
Okay,
so thanks a lot. I'll see you.
Yep.
Okay, bye.
Bye.